simulate the nota cell. I think we did it before, but let's repeat the previous simulation. Oops, this is not the one. 26. Yeah, for the 26 nota cell DC coupling. Oh yeah, this is the one. Yeah, what's in there? I think we looked at it already. Yeah, see, I have an inverter 10 thing is here. Is it? Oh yeah, how come this is just M equal 1? Just same as the inverter. And then, you know, those two are that input and the output connected together. And then X5 and X6 is that cross-coupled inverter, right? Inverter X, sub-circuit inverter X is there. So they have some mismatch. Oh, this thing has some mismatch, right? Not 1. It's 1.5. NMOS driver has channel length 50% longer. VDD2 is 3.2. Okay. Somehow I have only, let me see, let me change it back. Multiplication factor is still 10. This is previous simulation. Okay. All right. DC coupling. So my input is sine wave. My output is, my sine wave is distorted a lot. My output sine wave is distorted a lot. So actually, see, for the we can do the DC transfer curve. Somebody asked if I apply too much positive feedback by using larger supply voltage, I think you can observe some hysteresis. You know, if you have positive feedback, the transfer curve has some hysteresis, right? It will show something like a hysteresis characteristic. Okay, this is a lot of positive feedback. Simulate. Do I have some DC there? Oh yeah, this DC. Well, this DC transfer curve was 01, 02. Okay. Oh, this is still not very sharp, right? Say, what's my 01, 02? I1, I2 is there. So yeah, this is my GM3 is not large enough yet, right? Because see, I don't see any hysteresis at all, right? Let's increase GM3. So we just change this supply voltage, 5 volt. Wow, that's a lot. Then my GM3 will increase a lot, right? Simulate. Okay. Then this DC, how does my DC looks like? 01, 02. Can you see something similar to hysteresis? It's not exactly hysteresis. Oh, looks like some hysteresis. We are not sure, but let's see. Let's make it crazy, like 10 volt. Wow, it's a lot, too much. Huh? The circuit may break. Simulate. Then this DC curve is, let's see, how does the OP01 looks like? Wrong. Somehow it doesn't work. Very weird. Eh? Not even hysteresis, but doesn't work too much. Let's move it back like 4.0. I don't want some hysteresis like a characteristic. Simulate. I just want to increase the gain. differential mode gain. Let's see. Yeah, yeah, DC. 01, 02. Looks okay. I may even increase GM3. So it's still linear characteristic, right? Maybe I can increase it like 4.5. 4.5. Okay. What does it look like? Simulate. Okay, show me DC. 01, 02. I think there is some hysteresis-like characteristic already here, right? Too much gain. Is it too much gain? Yeah, too much gain. No good. 4. I have to reduce my. This is just a 4.2. Okay. My GM3 is too much. Simulate. Okay. Then let's see what happens. 01, 02. Yeah, looks fine. So this one is a linear, no hysteresis, right? So no hysteresis. Okay, just a large gain. Maybe we can look at the transient analysis. Oops. There was some transient there, right? DC tran. Oh yeah, this thing. Oh no, this thing. So what's a lot of distortion, right? Large distortion already. Too much gain. This small thing is input. Large swing is my output. So a lot of distortion, right? My sine wave is not pretty. But we can reduce this input. So let's see. Maybe we can reduce a little bit. Let's reduce my input. This is 50 millivolt. Oh yeah, make it 5 millivolt this time. 5 millivolt. What's my? Oh yeah, it's already there. This is already in the inverted format. So yeah, 5 millivolt. How does it look like? Transient. DC this thing. Yeah, my input is very small. How about my output? Yeah, my output looks more pretty this time. Not much distorted. Is it distorted already? It's already distorted. Not like a sine wave. Okay, so this is a differential input. Can I make this one into a common mode? Can I apply common mode input there? Let's see. Nota cell DC2. Okay. So how about the? Okay. So here's the. Let me see. I want to change this thing into sub-circuit. Like this is a dot sub CKT nota. What is my input? I1, I2, DD, DD2. Is it right? Yeah, there is a DD2 there. So I will change this thing into dot ends nota. And then see, oops. So I will generate a sub-circuit call X7, yeah, I1, I2, O1, O2, DD, DD2, nota. Okay, this is my nota. I will apply X8, similar sub-circuit call I3, I4. Oops, this should be O2, right? Not O1, O2. So O3, O4, DD, DD2, nota. Then I want to apply some common mode input this time. Let's see, how can I apply common mode input? This is This is not exactly synchronized. Okay. Okay. So here's I will eliminate the DC, just transient. Then VIP3, VIP2, I3, and then VIP IM2, PIM2, I4. This right? So I will, yeah, this is my common mode input, right? Then I want to observe O3, O4. VI3, I4, VO3, VO4. Okay, let's just simulate it. Do I have some error? Huh? Huh? Oh yeah, you're right. You save a lot of time. Thank you. So it matches, right? It matches. So let's just simulate this thing. Simulate. Okay. Then let's just see. Do I have a tran here? Yeah. So I have. Oh, how come it doesn't work? Looks like I have more errors there. LIS. What's my error? Oh, it succeeded. Oh, what happens? Oh, okay. Oh, yeah. Sorry, I simulated the wrong one. I must open burst DC2. Where is my DC2? It is DC2. Ooh, yeah. How come I have? Oh, yeah. This thing. I must call this one first. How come this is there is some problem? Oh, no. No, fine. Let's run this one. Okay, DC2. So yeah, I have so for the same input, this is a differential mode, this is a common mode. Common mode thing is a little bit, I3 is, no, I don't like I3. I04. Yeah, see, this large one is, large swing is a differential output. This thing is, they overlap the O3, O4. Those are small common mode output, right? Yeah, common mode gain is smaller, but non-zero, okay? I have a non-zero common mode output. That's a problem. Yeah, question. Notice there, they doesn't suppress the common mode, right? It amplifies the differential mode pretty well. Okay, any question?